Principles of steam turbine. Here the steam energy is converted mechanical work by expansion through the turbine. What do you mean by expansion? So what do you mean by expansion? Here if we consider a turbine, the steam enters here and is exhausted in the other end. Here when the steam enters at this part, the pressure is very high. When it travels through the turbine, at the end the pressure decreases. The reason behind is when the pressure decreases, the expansion in volume occurs. So this expansion is volume is used in turbine so to gain the kinetic energy required to move the generator. In a steam turbine, there are two major components for converting it into a rotary motion. One is the fixed blade and another is the moving blade. Fixed blades are also called as the nozzles. In each row, a fixed blade and moving blade is called as a stage. To explain, so let's see what are a fixed blade and a rotating blade. So here we can see the component that doesn't move are called as the fixed blade and the components that move are called as the rotating blade. So here the fixed blade are also called as the stator, and while it can be also called as a rotor, the rotating blades. In middle of these there is a central axis called in which the shaft of the turbine runs. This shaft is used to couple with the generator, which is then used to convert the rotary motion into electrical energy. Now let's see on a steam turbine system. A widely used steam turbine system is a CHP type, which is also called as a combined heat and power. This is also called as a cogeneration type steam turbine system. Here combined heat and power means the application is not only to get an electrical output but also to use the amount of heat exhaust from the turbine into a useful process. For example, a paper, a pulp industry or a sugar industry which uses the exhaust steam for doing their processes. So the efficiency of this type of turbine is much more higher. This is the oldest prime mover technology known to humankind. It ranges from 50 kilowatts to many hundreds in megawatts. The thermodynamic cycle based is on a Rankine cycle, and the most common types are a back pressure steam turbine and an extraction condensing steam turbine. Let's see what's a back pressure steam turbine. Here the steam exceeds the turbine at higher pressure than the atmospheric pressure. Usually what happens is the pressure at the inlet of the turbine is so much higher than the outlet of the turbine, but still the outlet of the turbine pressure is far more less than the atmospheric pressure. But in case of a back pressure turbine, the exhaust pressure is much higher than the atmospheric pressure. Here the advantages of this type of turbine is the simple configuration, low capital cost, low need of cooling water and high total efficiency. So how we can say that the efficiency of this turbine is higher? The mechanism happening here is, as the pressure here is much more greater than the atmospheric pressure. So this pressure here, as it's been more than the atmospheric pressure, can be used for any other purpose, like as I told, for a paper and pulp industry or for a sugar industry. So here what we do is the energy doesn't get wasted by simply condensing, but the pressure is still extracted for doing some other purpose, plus the turbine's mechanical energy can also be converted into electrical energy. Disadvantage would be a larger steam turbine is required. So to say, the back pressure turbine can also be told as a cogeneration type steam turbine, where electrical energy plus the energy extracted from the exhaust of turbine can be used for the process and the efficiency can be increased. So let's go forward and we can know about what's an extraction condensing steam turbine. Here the steam obtained by the extraction from an intermediate stage. Remaining steam is exhausted and relatively high capital cost and lower total efficiency is for this type of turbine. In this type of turbine, the useful steam that required for any process is taken up from an intermediate stage, while the last stage, the exhaust stage, is directly condensed. So the difference between the previous steam turbine, that is a back pressure steam turbine, and an extraction condensing steam turbine, would be the end part of the turbine, that is the steam outlet at the exhaust in a back pressure turbine doesn't get condensed, while here in the extraction condensing steam, the end steam, that is the outlet steam, gets condensed back into a water. So in this picture we can see something like these are the rotating blades, we can see the stationary blades. So here is the whole arrangement of a steam turbine. Right here we can see number of stages here, which will have both the rotating blade and the stationary blade. To be precise, this part has all the rotating blades, while this is the stator which has all the stationary blades. So all the rotating blades will come in between the stationary blades, and over them another half of the stator will be covering the whole turbines. On a broader perspective, the functionality of a steam turbine, and it can be classified into two types. One is an impulse type steam turbine and another is a reaction type steam turbine. Impulse type steam turbines were initially designed when turbines started to come into existence. So the initial design of a steam turbine was based on the impulsive action. So to explain impulsive steam turbine, let's see the following diagram. Here a stationary nozzle has the high pressure steam coming out from its nozzle, from where the steam which is injected, which is coming out from the stationary blades, hits the bucket of a rotary mechanical device. So what is an impulse steam turbine mechanism? The basic idea of an impulse turbine is that a jet of steam from a fixed nozzle pushes against the rotor blades and impels them forward. This mechanism is based on Newton's law, that is, anything which is in rest, when it's impulsed by a moving object, the object which is at rest gets the kinetic energy from the moving body and it also starts moving. So this is the mechanism of an impulsive action. Here the velocity of the steam is twice as fast as the velocity of the blade. Pressure drops take place in the fixed blade. Here what happens is, when the pressure from the steam hits the bucket or the blade, what happens, there is a huge pressure drop. And here the thing is, the velocity that we attain is much more higher. So let's see what's a single stage impulse turbine. This is a primitive type of impulse turbine that was initially designed. To know the characteristics, we go on. The turbine consists of a single rotor to which impulse blades are attached. The steam is fed through one or several convergent nozzles. If high velocity of steam is allowed to flow through one row of moving blades, it produces a rotor speed of 30,000 rpm, which is too high for practical use. Here the thing is, the rpm is increased but the energy extraction is very low. What happens is, for example, to know about this, let's go back to this. This is a single stage turbine. Here only a single bucket is there which gets the kinetic energy from a single nozzle. This type of mechanism was designed. So here we see that here the RPM is much more higher, but the potential energy is extracted is very low. So let's see the cross-section view of a rotor. The turbine, here we can see multiple stages, again a shaft running through it. Components of an impulse steam turbine are a casing, rotor, blades, stop and control valve, governor, oil baffle, steam baffle, bearings, gearbox and oil pumps. Okay, so we'll discuss about the parts as a whole when we complete what's an impulse turbine and a reaction type turbine, and then we'll move on to the components associated as a whole. So what's a reaction type steam turbine? A reaction turbine utilizes a jet of steam that flows from a nozzle on the rotor. Actually, the steam is directed into a moving blade by fixed blades designed to expand steam. The result is a small increase in velocity wherever that of a moving blades. So here in the schematic diagram we can see what are the differences between an impulse and a reaction turbine to understand the basic fundamental on which a turbine rotates. Here we see that in this part a fixed blade is powering the whole rotary motion of the turbine. But here in the reaction turbine, the fundamental here is because the presence of a fixed blade that we also call it as nozzle in a staged arrangement, the output coming from the rotating nozzle is something like this. Okay. To explain precisely, in an impulse turbine the fixed nozzle powers the rotating motion rotor. Here we can see the pressure that hits the rotor part and the pressure that comes out from the rotor part. Here the pressure that comes out from the rotor part, the energy still is more in an impulse turbine when it leaves from the rotor. But in the reaction turbine, mostly in the reaction turbine we have a mechanism called as stages. Here the thing is, the outlet pressure that comes from the rotor is again redirected using other fixed blades, which is again given into other set of rotating nozzles. As the stages increases, the size of the turbine increases. So to precisely say what is the difference between an impulse turbine and a reaction turbine is it, here the pressure that leaves the rotor in the impulse turbine is higher. That means the energy still is not being completely used. But in a reaction turbine, the pressure that leaves the rotor part, that is the last part of a turbine, is much less because it has been used in stages. And here the extraction of energy, that is the complete use of energy, is much more higher in a reaction turbine. Here in the pressure and velocity curve we can see the sudden decrease in pressure, but while in a reaction turbine the pressure is retained throughout the turbine, which helps in increasing the efficiency of the mechanism. So thus a reaction turbine is more preferred than an impulse turbine. But there is a small point to be noted in a reaction turbine. Reaction turbine cannot be completely sustained on a reaction mechanism. Initially, when in the first stage, when the steam enters through a fixed blade and hits the first rotor, at that part it has an impulsive action. So no reaction turbine can omit a fundamental law of an impulse mechanism. That means a reaction turbine has in the first stage an impulsive action, and when it progresses through the turbine it has the reaction mechanism. That means the pressure is extracted in stages in a reaction turbine. So now here we can see a various part in steam turbine. So first we'll see where the steam pipeline is located. Here we can see the steam pipeline. The inlet control valve is this part. The control valve controls the steam output. The stator we know. Okay, we'll see the rotors. These are the rotors. Okay, a very important thing to be noted down here is what's a journal bearing, what's a thrust bearing, and what are the bearing pedestals, and what is the difference between these type of bearings: a journal bearing, a thrust bearing, and a pedestal bearing. Okay, so to start with the type of bearings here, we have to first start with what's a pedestal bearing. To see here, we can see this part. Okay, this is the main crank on which your whole turbine sits on. That means the shaft of the turbine sits on a pedestal arrangement, a static arrangement that connects your turbine rotary shaft and the ground or the basement. Okay, this is a static body which has the whole turbine over it. Over the pedestal bearings, to assist the rotary motion, we have another bearing called as a journal bearing. Here we can see it here, this part. Okay, here the journal bearing we can see sits upon our pedestal. This part is a pedestal on which a journal bearing is coupled. Journal bearing usually assists the rotary motion so that a friction is reduced. And to know about a thrust bearing, okay, the thrust bearing is this part. Yeah, so thrust bearing is used to overcome the axial friction between the rotor and the pedestal. Okay, whenever a turbine rotates, there is an axial vibration in the turbine. To control that axial thrust inside the turbine, we used the thrust bearing. What happens is when your steam enters this part and it gets expand in this motion, what happens is there is a possibility of turbine moving in this manner like a zigzag. There is an axial thrust, right? To control this axial friction, we introduce a thrust bearing at two ends of a turbine. In case of a single pressure turbine, that is, there are two types of turbine. One is a single pressure turbine and a double pressure turbine. In a double pressure turbine, Here the axial vibration that we get cancelled by each other as the expansion of the steam is on both the side. But in case of a single pressure turbine, we have the expansion it only in one direction, so the probability of having an vibration will be more. So to assist or to eliminate any damage because of this axial vibration, we have the thrust bearings. What happens whenever the rotor part rotates and produces an axial vibration? The thrust bars are the first point of protection between any stator component and the rotor, thus helping to avoid any damage in the rotor part. The thrust bearing commonly used is a Kingsbury type thrust bearing that we can look on the net for more information. So to conclude here about the bearing types, first we have a pedestal, a static thing, and after on which a general bearing sits, and the thrust bearing are one which is used to avoid axial friction between the rotor and the stator. Now we move on towards where's the generator rotor. This part is the generator rotor and the coupling device between the generator and the rotor of the steam turbine. Steam bleeding or extractions are these pipelines, an intermediate part in a turbine from which the steam is extracted so that it can be moved to an intermediate turbine or to a low pressure turbine. The safety governor sits here somewhere in this part. The turning gear, that is the initial phase when the turbine is started up. So turning gear is used to provide the initial thrust, initial rotary motion to the steam turbine before the steam is directly used to provide the rotary motion. Okay, labyrinth packing is at the two ends of the turbine, where we have the rotor and stator meeting together so that the steam that comes into the turbine doesn't escape. So to avoid a pressure drop in the turbine and to avoid any leakage in the turbine, we use labyrinth type packing. A main pump is used for providing the necessary lubrications in the turbine system. A centrifugal governor is some sort of here we can find the centrifugal governor. A centrifugal governor is a mechanical type of protection that we have in the steam turbine. Initially in the primitive days, the centrifugal governor were used as the only method for controlling the speed of a turbine. In a centrifugal turbine, it is a mechanism that works on the rotary motion of two balls connected over a stator. Whenever a stator rotates, this ball also rotates in a motion. As the speed of the rotor increases, because of this fly ball, what happens is a lever that's connected between the main shaft and the steam inlet is also affected. What happens is when the turbine speed increases, the flywheel goes up because of the centrifugal force, and because of which a steam valve is opened or closed accordingly so as to control the steam. To say precisely, centrifugal governor are the primitive type control system that were used to control the steam, the speed of a turbine, which is still in use in case any instrumentation or an electrical interlock fails. The centrifugal governor will come into picture to avoid any overspeed of the turbine. Few problems that we see in steam turbines are stress corrosion, cracking, corrosion fatigue, pitting, oil lubrication. Imbalance of the rotor can lead to vibration, misalignment, and thermal fatigues. These are more related to mechanical projection of steam turbine. So here, for our point of view, we will see like the oil lubrication is a problem in a steam turbine, which will be of our interest, and an imbalance in the rotor can lead to a vibration. So possibly in a steam turbine, monitoring of vibration is of a very important thing which we should measure in a rotary body. So only these two parts will be much more of our interest in the instrumentation. Yeah, that's for the session. Hope it has helped you out in understanding at least the steam turbines construction. In the next session, we will be moving on to the control valves and the major controls that we do in a steam turbine. Thank you.